Hello folks, welcome back to Merrill Math. I'm Mr. Merrill, and today we're going to be finding a quadratic that fits three given points, and we're going to be using a system of equations. So this is kind of an extension of the Lagrange interpolation video where we were given 3 points and we tried to find a polynomial. It ended up being a quadratic that would fit those points. So in this video we're going to attack that same problem, but we're going to be doing it in a different way. So the general form of our equation, like we saw in the last video, is y equals ax squared plus bx plus c. For this problem I'm going to be using capital A, capital B, capital C, just because when we're dealing with the system of equations it makes it easier when we're dealing with capital letters. You may choose to use lowercase or uppercase. This is just something that makes it easier for me to keep track of. Okay, so same situation as last time. We're going to be finding a quadratic function that contains these given points. So this is the same set of points that we were given in the last problem, and what we have to do is first start setting up our system of equations, and then we're going to go through solving a system of 3 equations. Now this looks like a difficult type of problem to tackle, primarily because there's a whole lot of stuff going on, but for this problem it's actually pretty straightforward. The points that we're given are x and y coordinates. That's your x, that's your y, here's an x, here's a y, and each of these points is going to fit into this equation here. So they're all going to look slightly different, but they're all going to follow the same format. So I have a y here, that goes there. I have an x here, that goes there and there. And then we can work through that. So we're going to start with our first point. So I've got y equals, so -2 equals a times x squared, so that's going to be 1 squared, plus b times x, which is 1, plus c. When I do my substitutions, what I usually do is put the number that I'm substituting. In this case it's the x. I don't do it for the y because it's just kind of there by itself. But I put the x in parentheses just to let me know that that's something that I still need to work out. Now in this case it's fairly easy because 1 squared is 1 and b times 1 is just b. So this just says -2 is equal to a plus b plus c. So this one we're going to kind of mark a little bit. We're going to give it some stars and say, like, okay, this is our first equation that we're going to be using. Our second equation, we're going to use our second point. So we have y, which is 1, is equal to a times -2 squared plus b times -2 plus c. So in this case we got a little bit of work to do here. So 1 is equal to -2 squared is 4, and -2b. So in this case, I got a little carried away with my plus. We could just say plus -2b, or a better way to do this is just to say minus 2b plus c. So that's an easier way to look at this. So again, we're going to kind of mark this one so we know that that's another equation that we're working with. Our last one, the point was 3, 6. So we have y, which was 6, is equal to a times 3 squared plus b times 3 plus c. Okay, so for this I've got 6 is, we'll call that 9a plus 3b plus c, and this is another equation that we're working with. Now this method, because it's a system of equations, it's going to, like most systems of equations, take up a fair amount of room, so we kind of have to be prepared for that. So the next bit that we're looking at, I'm going to kind of switch papers here. So we're going to take our three equations that we were dealing with. So we have -2 is equal to a plus b plus c. We have 1 is equal to 4a minus 2b plus c. And we have 6 is equal to 9a plus 3b plus c. Now this is quite a bit different than the Lagrange interpolation, but we can see that we also kind of have our work cut out for us here because it's a system of three equations and three variables. Now when we're doing this, we're doing systems of equations. What we're looking for is a set of three numbers, a, b, and c, that make all of these equations true. So in this case, we have a lot of options when we go to solve problems like these. So for systems of equations, I think there's probably 4 generally accepted like major ways that we can do this. We could graph them. Now this would be I guess a line in 3 dimensions, so those are kind of awkward to graph. So we're not going to do that. We can use a method called substitution, or a method called elimination, or we could use matrices. We're not going to be talking about all of those methods today. I'm just going to tackle this with substitution because most students, when they're doing systems of equations, they're either forced to do substitution or elimination. Substitution is just the first one that gets taught, so and I don't think I have a system of equations video posted yet. Way back in the old Merrill Math Channel days, I think my very first video was systems of equations, but that's been taken down. So, or I took it down. It wasn't like a copyright. Somebody has a copyright on systems of equations. So what we're going to do is substitution. So what I'm going to do is take this first equation and just solve it for a variable. I'm going to solve it for c. We could solve it for a or b. It doesn't matter. But I'm just going to solve this for c, just because it fits in nicely with these other ones. So then we end up with a system of 2 equations. So I solve it in this one, and then I substitute that value into these equations. And then I can do another substitution step where I solve for either a or b, and then I substitute that into the last equation. And then I end up with a variable that I can substitute back, and then substitute back. It's kind of like sort of walking up a flight of stairs and then back down. It kind of feels that way. So you're sort of walking forwards and backwards through this method. So I need to solve for this c, which means I just need to subtract these pieces from the side. So in this case, I could say that this equation yields c is equal to -2 minus a minus b. So that's what we're going to use for these equations. So this value right here is going to go into these equations for c, because c is equal to that. And now we notice that we've reduced both of these equations to just a's and b's, because there's only an a and a b in here. There's an a, b, and there will be an a and b in there, an a and b in there, and then we can kind of move forward with this method. So this equation, so for equation, we'll call this equation 2, we've got 1 is equal to 4a minus 2b plus c, which is -2 minus a minus b. And then we can sort of combine some stuff. Let me see if I have some room here. So in this case, I've got 4a minus a, that's 3a, -2b minus b, that's -3b, and I've got a -2 that I can sort of jump over to the other side. So I'm going to say 3. Actually, I'm going to flip this because working with the number on the left-hand side is kind of weird. I don't know why I've been doing this whole time. You can do that, it's fine. I just sort of work with the number on the right-hand side. So let's do it this way. So 4a minus a, that's going to be 3a. -2b minus b, that's -3b. And that's all equal to 3. And that actually lets us simplify this down a little bit more. So I have this piece, for now, so I'm going to kind of mark that so I know to come back to it. This equation we also have to substitute into. So I have 9a plus 3b plus c, and I'm going to substitute this in. So I've got 6 is equal to 9a plus 3b plus c, which is my -2, -a, -b. So I can do some combining of like terms here, and this equation is going to yield 9a minus a, that's 8a, 3b minus b, that's 2b, and this -2 is going to come over to the other side and add to the other side. So the way to get rid of it from here, we add it to the other side. So we're going to say plus is a +8. And this is another equation that we're going to come back to. So we have 3a minus 3b equals 3. We have 8a plus 2b equals 8. Now both of these equations, there's actually a simplification that we can do here. So what we're going to do is sort of divide a common factor out just to start, because it's just easier to deal with. All of these terms divide by 3. So this equation kind of comes down here and becomes 3a divided by 3. That's going to be a minus b equals 1. So we're dealing with this one. And this equation, everything is even, so it's all divisible by 2. So I can say 4a plus b is equal to 4. Now, just because fortune has smiled upon us, I'm going to combine this method with a little bit of elimination. So whenever you get a situation in a system of equations where one of your equations is, in this case I have a minus b and a plus b, where the same variable has the same coefficient in front of it but opposite signs, what we can do is, in a sense, just add the equations vertically. So I have, because I can add the same thing to both sides, so in this case a minus b I'm adding to the left hand side here, and 1 is what I'm adding to the right hand side here, and those aren't different values. So I'm still adding the same thing to both sides because there's an equal sign here. So they're both equal. So I'm adding the same thing to both sides. It just looks different. So 4a plus a is 5a. And 4 plus 1 is 5. So that tells us that a is equal to 1. So far, this is the first result that we've gotten in our system of equations. So we know, if we come back to our original system, we know that these a's are all 1s. And then we can go back and solve for the other ones. So if I know that a is equal to 1, that means it's equal to 1 in both of these. So that tells me that a minus b is equal to 1, which means that 1 minus b is equal to 1. If I subtract 1 from both sides, that tells me that negative b is 0, or just b is equal to 0. So that's our second piece. So we have 2 pieces, and we can, I'm sorry because we're kind of jumping around here, that sort of happens with systems of equations. You have to keep track of a bunch of things and sort of mark stuff to come back to it later. So back here, we know that a is 1 and b is 0. So now we just have to figure out what c is. Well, that's -2 minus 1 minus 0. So -2 minus 1, that's going to be -3. So c is equal to -3. So those are all of our pieces. So let's sort of combine this together into our original equation. So we know we want something of the form y equals ax squared plus bx plus c. We know that this is 1, this is 0, and this is a -3. So that tells us that y is equal to ax squared, so that's just 1 times x squared plus 0x, which is just 0, minus 3. Now this is our function for our quadratic function that contains these 3 points. So the points are 1, -2, -2, 1, and 3, 6. And like we found in the Lagrange video, we ended up with the same function, x squared minus 3. So if we square 1, subtract 3, we're good. Square that, 4 minus 3, that's 1. Square 3, that's 9, minus 3. So all of these points check out, and that's what we want. Now, is this necessarily the only function that goes through those 3 points? Not necessarily. I would imagine that there are other functions that will go through it, ones that are more complicated, maybe ones that have a higher degree. But what this allows us to find is one of the simpler polynomials, or one of the simpler functions that goes through those points. So using a system of equations to solve a Lagrange type problem, some students might find it a little bit easier to deal with because, well, one, we didn't have to go through all that FOIL mess and finding common denominators and stuff. I actually skipped that in that video. So, I mean, I did it when I worked it all out by hand before the video, but I sort of spared you guys all of that nonsense. Plus, if you have a calculator that will do that, then the chances are you would just do that. I grew up using a TI-89, so that's the calculator I recommend using. So, at any rate, using a system of equations to find a quadratic function that fits a set of 3 points, that's how we do it. If you have any questions, comments, points of clarification, you can add those to the comments. Thanks for watching.